Welcome. So, in our first lesson here, we're going to introduce a new set of coordinates to put on our two-dimensional plane. Right? So what you've probably been using, maybe even exclusively up to this point, are what are called Cartesian coordinates, where you have, like an XY plane, X being the horizontal direction and Y being the vertical direction, right? So we often call these rectangular coordinates because you can sort of like move along the edges of a rectangle to get from, point to point here. And if you look at the grid that, say, a sheet of graph paper would give you, I mean, there's squares here, but squares are just special rectangles. All right. So this is usually a great way to think about the plane. The coordinate plane, right? It tells us, uniquely where exactly we are at any place in the plane we want to be. There's a set of coordinates for it. But the fact that these are kind of based off rectangles can make describing certain equations pretty hard, right? I mean, think of linear graphs, right? Linear graphs are really simple, just y equals mx plus b. But when you start getting to non-linear things like, conic sections, circles, ellipses, hyperboloids, and stuff like that, the equations get a bit more complicated. They're not impossible to deal with, but they're a little more complicated, right? You start getting quadratic terms and so on. Well, we're going to look at something even more complicated than that. Or at least it seems that way at first. Right? Here's an example of a graph we want to look at. We want to be able to describe. Right? This thing here that sort of looks like a flower. In fact, we usually call these roses. This would be a rose with 5 petals. Right? So imagine trying to describe this in Cartesian coordinates. Right? First off, it's not a function because it doesn't anywhere near pass the vertical line test. But even just trying to describe this, like the weird angles that everything goes at, it's, pretty difficult to do. But this kind of graph and these sort of like curvy circular graphs that'll make some more sense in a bit, these are very natural to show up. One example is in orbital mechanics. How planets or satellites orbit objects, right? They orbit in an ellipse, or sometimes a parabola, if you're talking about a comet. So we want good ways to describe those kind of things as a function, right? So how can we do that? Well, we need a new set of coordinates. These coordinates are going to be called polar coordinates because they're going to be based off of we'll have a pole. Think of like North Pole, South Pole kind of thing. And then, so we'll have a pole. That's our standard starting reference point. And then we're going to measure distance away from that pole. And we're also going to measure angle with respect to some axis. Right? So polar coordinates, what they're attempting to do is to describe the plane not based off of rectangular positions, but circular positions. Right? So it also consists of two numbers, right? So it's a pair of coordinates. How do these work? Well, so we're going to call our two variables, our two coordinates, r and theta, right? And the pole in this case, usually we call the pole O. That will be the origin, right? And that's going to be right here for us. Okay? So, my mouse cursor just now showed up, by the way. It wasn't showing up earlier. Anyway, so what are these two numbers going to measure? Well, R is going to measure, say this is our position here, this red dot. R will measure how far away from the pole we are. In this case, in the standard form here, how far from the origin are we? And theta is going to measure how far from the positive x-axis have we rotated. Right? So counterclockwise is positive theta values. Clockwise is negative theta values. Right? So how do we see this work out here? So let me open this up so you can see here's the value of r, here's the value of theta. I think this should be pi over 4. But as we make r bigger, right, the dot gets further from the origin. Notice how the angle doesn't change. It just gets further, or if we make r smaller, it gets closer to the origin. Right, that's how r works. Theta, if we increase it in the positive direction, it rotates counterclockwise, and it'll keep going, right? So, if you make it 6 pi, it's going to still be on the x-axis, but it's going to have wrapped around 3 times. Right? If we make theta negative, right? So like here, this is, I don't know, pretty close to like a, would this be negative 7 pi over 4? Right? Because we've wrapped around the opposite way. Now what happens if we make r negative? So think about what might happen. So when we make r negative, remember, if we make it bigger, it gets further away. If we make it smaller, it gets closer. So if you kind of just base this off of how it's changing, when we go negative, it shouldn't surprise you that we actually end up going the opposite direction as the angle. So the angle here is telling us, okay, go up to almost pi over 4 here. But since r is negative, instead of going in the normal direction, we go backwards. Right? That's all negative r means, is find your angle theta and then move backwards. Right? So, one important thing to know about polar coordinates is that they're not unique. They're very not unique. Right? So if we have a point, say like 2 comma pi over 4, if we just add pi over 2 to that set of coordinates and get 2 comma 9 pi over 4, it's going to be the same point. Or we could subtract 2 pi, or we could add any multiple of 2 pi, positive or negative. We could also say, let's say here we go to negative 2. Oh, I broke it. Oh. Exactly how I broke it, but I did. Alright. So another thing we could do is if we're at, 2, and our point is down here, if we, switch the angle so that it's up here instead, right, and then make r negative 2, we end up in about the same spot. Right, hard to get the exact number here. Yeah, so the point is, there's many different ways we can represent the same point, polar coordinates. So the price we pay for moving from this nice rectangular picture to what's usually a more convenient coordinate system is we lose some of this uniqueness we had, which is usually a worthwhile price to pay. Right? Yeah, so here's a couple ways in which coordinates which polar coordinates can be duplicated. Usually, though, when we're picking points, we want to keep a positive r value and pick theta to be somewhere between 0 and 2 pi. Right? Just because those are sort of the nicest numbers to use. Right? Though we often do want to use other ones. It really depends on the situation. Right? So rectangular coordinates give us graph paper that sort of looks like a bunch of squares. What we get with polar coordinates are these circles here. Right, so we get a bunch of circles. Let me shrink this a bit. We get a bunch of circles. These represent the different r values. So like r equals 1, r equals 2, r equals 3, r equals 4. And these other lines here, these sort of radial lines, this would be like theta equals 0, theta equals pi over 12, pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2, and so on. Right? You've probably seen a picture like this when you've studied like the unit circle before. Right? But this is our new graph paper. Right? The circles represent the r value. These radial lines represent the theta value. So in the next video, we'll talk about conversions between polar and Cartesian coordinates. And then after that, we'll talk about graphing in polar coordinates.